Thank you for the kind introduction and welcome to my presentation. So the work I'm going to present is based on the PhD thesis of my former PhD students Peter Regier and Lily Bruckschen. So service robots acting in human environments should avoid interferences with the users and act foresightedly, which means that they should adapt their behavior to the users and not vice versa. And here you see 3 examples of undesired behavior. So in this situation here, the robot is kind of blocking the way of the user. So both user and robot are somehow in a stuck situation. In the second situation, the robot is closely following the user, which might be annoying. And in the third situation, the robot is too far away, so no fast reaction is possible in case that help or service is needed. And we want to avoid such situations during service robot operation in human environments, and I'm going to present our approaches how to solve this problem. Furthermore, robots should not just treat objects as static obstacles, but distinguish between different types of obstacles and reason about possible actions, how to overcome the objects. So in this example here, these blocks, for example, can be stepped over by the robot, balls can be kicked away, and like the stuffed toys here, can be moved or carried out of the way. And the robot should reason about different obstacle types and then choose appropriate actions to free its path. So problems to be solved by service robots acting in human environments are first, motion planning and navigation through cluttered regions with many objects on the floor, the robot has to move through, so possibly by moving the objects aside or by stepping over or onto them. And second, the robot needs to predict humans' motion in order to improve its own behavior. So it needs to anticipate when and where its assistance is actually needed, and as well as it should avoid interferences with the user during navigation. And I will, in the following, present 2 approaches we recently developed as solutions to these problems here. But first, since you are probably not so familiar with sensor data the robot is acquiring and which is needed to decide on the action of the robot, I would like to introduce you to how the robot actually perceives the world around it. So here you see one of our robots, which is equipped with an RGBD camera on top of its head. And to illustrate what kind of observation data the robot is dealing with, consider the following scene. So the robot is standing in front of a plant. In the background are also some objects. And this is a current camera view of the camera on top of the robot. And using recent segmentation methods from computer vision, we can obtain estimates about the different object classes. So we can obtain information about the different objects. So the robot knows that this is a chair, this is a table, this is a plant, this is like a sweet pepper, these are leaves, and so on. So we can analyze the RGB image of the robot using image segmentation methods and get information about the objects in front of the robot. And the camera additionally has a depth channel. And from the depth channel, we get depth data, so distance information about the obstacles in the environment. And the robot can then infer the relative distance and size of the visible objects. And to illustrate how this depth data looks like, I have the following example here. So on the right, you see a visualization of the depth data obtained with the robot's camera. And depth data gives information about the distance of the individual points in the environment. So for example, here these red pixels correspond to points which are close, so like these leaves here. And then we have like medium distance points and far away, so more distance points as illustrated by the green and black pixels here. And since depth cameras have only a certain range in which they can measure the objects, we have many unknown areas here because the areas which are in the field of view of the RGB camera, those objects are too far away from the robot, so not visible in the depth image. So to summarize, from the RGBD sensor, we can estimate semantic labels corresponding to object classes in the RGB image, like here. We know that this is a sweet pepper. And from the depth image, we get distance information about the detected objects. So using a combination of color and depth data, we have an estimate about the type, relative position, so distance, and the size of the detected objects. And the robot can then use this information for navigating in the environment. So coming back to our original problem. So we want to perform motion planning of the robot. How do robots solve navigation tasks? So here you see a bird's eye view of an environment, like a sofa, desk, lamp, a plant, and so on. And what we typically do in robotics is that we discretize the environment to calculate a path for the robot from its current position to the goal location. So discretization of the environment means that we put like a grid onto the environment and then calculate a cost grid that is used for motion planning. So we approximate the environment as a 2D grid and then calculate costs for the individual cells and calculate a path for the robot from its current location to the goal location. So to obtain costs for the individual grid cells, in the first step, we mark each grid cell that is occupied by a static obstacle as non-traversable. So all these black cells here correspond to non-traversable areas. I go back one slide, so correspondency. So all the black cells correspond to static obstacles in the environment. The corresponding cells are marked as non-traversable for the robot in the cost grid. And the navigation costs of the remaining cells first depend on the distance to the obstacles. So the closer a cell is to a static obstacle, the higher its cost. So with that, we indicate that these cells are like dangerous since collisions of the robot with the obstacles might occur. And second, the cost of the remaining cells depend on the time to execute actions. And then we calculate the best path in the cost grid of the robot. And the best path is the one with the cheapest costs. And the path costs are basically just the sum of the cells, the sum of the cell costs on the path. So in this example here, the green one would be the cheapest path from the current position to the robot's goal location. And this is a general principle which is applied in robot motion planning to calculate the path of the robot from the current position to the goal location. We always have to calculate such cost grids and then perform path planning, so finding the cheapest path in this cost grid. So, as I said before, robots acting in human environments need to be able to navigate through cluttered regions where there are many objects on the floor, and the robot has to reason about how to overcome these objects. So the robot might also need to move objects aside to free paths, which involves whole body motion planning. So the robot needs to plan motion for its whole body, including the arms and the legs. And it needs to also pick up objects to free paths, for example. And the challenge here is that finding a detailed plan of all needed actions and planning all the whole body motions is computationally expensive. And therefore, we exploit knowledge about different obstacle classes to choose appropriate robot actions. So in this example, the robot has to navigate through an area where objects are blocking its way to the goal. And here the robot can either decide to pick up and move aside the stuffed toy here, or it can, for example, perform footstep planning over these toy blocks here. In this case, the robot would decide to pick up the stuffed toy and move it aside and then continue walking. And the question is, how is this kind of planning realized? And I want to explain you the approach we developed in the following. So our approach combines path planning, footstep planning, and object manipulation in one framework. We use a convolutional neural network for pixel-wise segmentation of the RGBD image, and in this way obtain the information about the obstacle classes. Then for each object class, we estimate the costs of the corresponding actions to overcome the obstacles. And the action costs depend on the execution time the robot needs to execute the action. Finally, we then encode the action costs in a 2D cost grid map of the environment and use this map for fast path planning as shown before. And this path then implicitly contains the necessary actions the robot needs to carry out to reach its goal location. I will present the individual steps in the following in more detail. So we use the Bonnet library to train a convolutional neural network to obtain the pixel-wise object segmentation in the RGBD image and estimate the object class. Here's an example for a book that is in the RGBD image and segmented using the CNN. Then we need to define actions for the different obstacle classes. So these actions have to be chosen for the used robot type. In our case, we use a humanoid robot, which is called Now. You've seen it on the images before. And the application we were considering here is navigation through children's rooms with toys on the ground. And correspondingly, we use the following object classes and associated actions. So balls, for example, can be pushed or kicked away, can be stepped over and also picked up. Cars or toy blocks can be stepped over or picked up. Stuffed toys and dolls can be picked up and moved aside. And boxes and books can be stepped onto by the robot. Of course, if you use a different type of robot, which can perform or has different capabilities, then we can define other actions or use also other object classes and assign the corresponding actions and their costs. So we use depth data to exclude actions depending on the size of objects. So from the depth data, as I said, we can estimate the volume of the objects. And for example, if the robot, using the depth data, the robot can infer whether an object has maybe a too large volume, so like a toy car is too large to be stepped over, then the robot can pick it up, for example. And obstacles with an unknown class or no executable action are considered as static, so as not movable by the robot. So the corresponding cell would be marked as non-traversable by the robot. And in the end, we assign the cheapest possible action to each detected object in the RGB image. As I said, the action costs depend on the time that is needed by the robot to execute the corresponding action. So we define the cost of the actions according to the estimated completion time. And for that, we measured the time it took the robot to reach a goal in a certain distance by just walking straight, by kicking away a ball, and by stepping onto an object and moving aside an object. So based on the average execution times, we define costs for the individual actions. Now, how can we use the obstacle information for path planning? So we project the object detected in the RGB image with their corresponding action costs onto the mentioned cost grid. And then we search for the cheapest path in the cost grid to the robot's goal location. And this path then contains the necessary actions that need to be carried out by the robot to reach its goal. I have an example on the next slides. So here, this is a current camera view of the robot. And as I said, we first segment the RGB image with a convolutional neural network that we have learned before. So we know, or the robot knows, that this here is a doll, that these are toy blocks, and the corresponding segmented RGB image looks like follows, where the individual pixels are marked with the object class where they belong to. Using the information from the depth channel of the camera, we have information about the distance of the obstacles, and we can use this information to determine the location of the object in the 2D map using the steps data. So basically we project the object onto the ground. So we have an estimate about their relative position and size and can use this to project the information onto the ground. So here the yellow cells corresponds to the baby doll and the brown cells corresponds to those toy blocks here. This is just a projection onto the 2D grid of the environment. And actually this here is the robot pose as indicated. And from this pose, the robot obtained this camera view here to get you an idea how this projection is performed. And as you see here, the wall visible in the robot's camera view, which corresponds to this wall here. And using the corresponding grid, we now insert actions that are needed to free the path of the robot corresponding to the objects. In this case, the robot can either step over the toy blocks in this area or move aside the baby doll when it traverses this area. So the robot performs or uses this cost map to perform path planning to its goal location. As you see in this situation, the cheapest path leads across the toy blocks. So the robot would choose a path here to step over the toy blocks, which is cheaper than moving aside the baby doll in this case here, as indicated by the darker gray cost here. So we have lighter gray costs in this area, so it's cheaper to or faster to perform footstep planning over the toy blocks in comparison to moving aside the baby doll. So we have a plan that can now be executed by the robot with local action execution to reach its goal location. And how does this action execution or plan execution work? So basically we split the whole plan into different parts. For path segments where there are no objects, the robot just has to follow the 2D path. So it does not have to perform any actions related to objects. It can just follow the standard walk and control the 2D path. For the other actions, the robot has to execute local reactive action execution. So for pushing actions or pickup actions, the robot walks to the last free grid cell on the 2D path and then executes the corresponding action using its current observations. So using the segmented point cloud, it identifies the exact location of the objects and then pushes it away or picks it up and puts it away. And for step over or onto actions, the robot would perform footstep planning in the corresponding region of the environment, also using the current observations then calculated from the point cloud of the RGBD sensor. I show you an example in this video. So on top, you see here an overview of the scene. The robot's task is to move from its current position to some goal location down here. Here you see the grid map of the environment. Initially, there are just the static obstacles contained in the map because the robot cannot observe the obstacles here. But when I start the video, you will see how the robot perceives the environment and then updates the cost grid and plans its actions. So I start the video now. Hopefully it will start. Yeah, there was some movement, there's some delay. Okay, so the robot starts walking and then will detect parts of the toy blocks, which will be inserted in the map here, and also the stuffed toys map. So initially, the cheapest path leads over the toy blocks, but then the robot detects that there are more toy blocks on the way, and now the cheapest path actually leads through the stuffed toy. So the robot decides to pick up the stuffed toy and move it aside, because this appears to be cheaper, so to be faster executable than footstep planning over the set of toy blocks here. So now the path is free. The robot updated its cost map and continues walking towards its goal location. Now we see a second scene here. The robot has mapped this ball and this, what is it? I don't know. And here it's like a box, and here it appeared cheaper for the robot to push away, pick away the ball, then stepping over the box. And as you see, the robot is able to reach its goal location. Here it's still red because the ball has returned. The robot kicked it away, it returned, so it's still here in its field of view, somewhere down here, but it does not impede its way to the goal anymore, so the robot would be able to reach its goal location. So I have a second video here with a humanoid robot in simulation. Here you see that the path of the robot leads over those toy blocks, over those blocks here, where the robot has to perform footstep planning and step over them. So the robot follows the calculated path close to the blocks, but then the footstep planner cannot find a solution about the blocks since they are too close. So the robot has to replan using its current observations and change the action. So the robot decides to move aside the first block and free the way and can perform footstep planning afterwards to calculate or to continue its path to the goal. Okay, so I've shown you our approach to realize like navigations through cluttered scenes using planning on a cost grid. Now I come to the second part of my presentation, which is about human motion prediction and foresighted robot navigation. So the prediction of human movements is important for a service robot to anticipate when and where service is needed, as well as to avoid interferences during navigation. And one observation is that humans typically move between different objects and interact with them. And our goal is to utilize this observation or this knowledge to generate foresighted navigation behavior for a service robot. So the goal is that the robot is close to the user in case help is needed, but at the same time avoid interferences or avoid being too close to the user. And in this example, you see the robot is, the user is interacting with the cat. And the most likely next object the user interacts with is this table here in this example. Accordingly, the robot would move close to the table to be able to provide quickly assistance if needed, but at the same time keep distance to the user to not interfere with the user. And I will present our approach, how we solve this problem of achieving foresighted robot navigation behavior. So first, we learn transition probabilities for object interactions. So basically, we answer the question, if a human interact with an object A, how likely it is that the user will interact next with object B. So these are transition probabilities for user-object interactions. And we use a map of the environment with the location of relevant objects. And we also integrate observations about the user and detected object interactions to predict the user's next navigation goal. And this knowledge can then be used to realize foresighted robot navigation by choosing robot poses that are close to the user's navigation goal while avoiding interferences with the robot's predicted motions. So I will present the individual step how we approach this problem in the following slides. Okay, so to learn transitions of object interactions, we developed an approach to extract general object interactions from RGBD video streams. Again, we train a convolutional neural network to detect objects in the RGBD images. And additionally, we use the open pose system for the detection of users, so for the detection of humans and estimation of their body poses. And we detect interactions based on objects the user is oriented to and objects that are touched. So we estimate the user's orientation and the hand position from the body pose, and then check whether there's an overlap between the bounding box of detected objects and the hand positions, and whether they are close in depth. And then we have an object interactions. I show you the example here. So the green dots corresponds to the estimated body pose of the user. We have here detected objects in the environment, and you see here that the bounding box of the hand and the bounding box of the object overlap, and additionally user is oriented towards the coffee machine, and therefore our system would detect an interaction with the coffee machine. This video illustrates how interactions are detected from the RGBD video stream. So on the left, you will see detected object interactions. They will be highlighted as soon as I start the video. And on the right, you see the detected person, their body pose, and detected relevant objects. So I start the video. You will first see here an interaction, a detected interaction with the laptop, then a detected interaction with the cup, and finally a detected interaction with the coffee machine. So using the system, the robot can infer objects the user is interacting with. And from the extracted human object interactions, we then derive transition probabilities between objects. So basically, we count how often the user traversed from object A to object B and to object C and so on. So these probabilities tell us if the user interacted with object A, the probability distribution of the next object the user will interact with. And using knowledge about the locations of relevant objects in the environment, we can then infer likely navigation goals of the user and predict human motions. So this example here, the user is again interacting with the cup. The user's position in the environment is this one here. Again, consider a bird's eye view of the environment. So the user is here, the robot is here. This is a current camera view of the robot. The robot detects the user interacting with the cup, and based on the information about the relevant objects in the environment, the robot can then infer that the user is most probably moving to a coffee machine, indicated with C here, or with a table, or interacting with the sofa in the next time steps. So the robot knows about the next objects the user will interact with using the learned transition probabilities of user-object interactions. And given then such a map of the environment, the robot can infer where the robot is moving to and can use this information to determine its own navigation behavior. So we also integrate observations about the user's movements and their pose. And we update the probabilities of possible user navigation goals using Bayesian inference, as explained in the following. So our goal is that the robot can estimate the user's next navigation goal. So we want to calculate the probability distribution over the user's next navigation goal, which means that for each known object in the environment, we calculate the probability that this is the next navigation goal of the user, given its currently observed position and pose. So this here is the information the robot observes. It observes the user position and its pose, and also the object interaction. And from that, it wants to infer the next navigation goal of the user, which is one of the objects in the environment. And to calculate that, we apply the so-called Bayes rule, which we often use in robotics to do inference. And Bayes rule means that we here calculate this probability distribution as a probability distribution corresponding to the likelihood of the user position and pose, given that object OI was a navigation goal, times the prior probability of OI being the navigation goal. This is a bit mathematically, I know, but I just want to show you that we also work with formulas in our research. So this here corresponds to the learned interaction model, which tells us the transition probabilities of the user between the individual objects. So this here, this ISC, are the learned interaction transitions. And this is the observed object interaction that's currently observed, the last object the user interacted with. And this here gives us a probability distribution over the next object that the user will move to. And this here is the observation model. So assume that object OI was a navigation goal. How likely is the current observation about the user position and pose? And this is calculated using the inverse distance of the user to the object and also the inverse orientation difference of the user towards the object. So basically, the closer the user to the object, the more likely it is that the user will interact with the object next. So now we have all terms to calculate the belief about the next navigation goal of the user. We have here the interaction model to get the distribution about the next object the user will interact with, given the currently observed object interaction. And we have here the observation model to evaluate the current observation of the user, taking into account the object positions. And in this way, we get a probability distribution about the next navigation goal of the user. So all this was just to illustrate how we can calculate the next navigation goal of the user. So we evaluated our approach in regards to how it can predict the navigation goal of the user. So after each observation and update step, we check whether the predicted most likely navigation goal corresponds to the user's true navigation goal. We did this in simulation. So we count a prediction as correct using two metrics. First, we use a prediction accuracy, which is the number of correct predictions divided by the total number of observations. So this gives us the prediction accuracy. And then we also evaluate the average position on the user's trajectory, from which on our system continuously returns the correct navigation goal. So we evaluated that using a data set of 64 human trajectories, which we collected in 25 simulated home or office environments. And it came out that we achieve a prediction accuracy of 0.67, and that our system returns the correct navigation goal of the user after having observed like 28% of the trajectory. So our approach works quite well. And the question is now how we use the prediction to improve the robot's behavior. So we want to use the belief about the user's navigation goal to determine the best robot position. As I said before, a robot needs to place itself close to the user, so in case service is needed to be able to quickly react. And so we evaluate grid cells again using a cost function. And here we take into account the distance to the user's possible navigation goals, weighted by the corresponding probabilities. So basically here you see the green objects are likely navigation goals, and the robot then chooses as position for itself a location that is basically close to all most likely navigation goals, so that the robot would, when the robot positions itself there, it can quickly react to the user. And for navigating to this position, the robot considers constraints which are derived from studies about human comfort during navigation. And there are actually 3 areas that are relevant. So 2 areas that the robot should not enter, which is like the social zone, which corresponds to a circle with a radius of 1.2 meters around the user, which the robot should not enter. Then we have the information process space, which robot should also not enter. This is kind of interperson, or objects in this area are considered as obstacles. So the robot or other people should not enter this area here in front of the robot. And we have an area with increased cost behind the user, because humans do not like if the robot follows too closely. So while the robot navigates to its best position, where it wants to position itself, it considers the human predicted motions and avoids the corresponding zones to not be too close to the user. So this video shows how the approach works in practice. On the left, you will always see either the front RGBD camera of the robot or the back camera. This is again a top view, a bird's eye view of the environment. The user is indicated as this here, and this here is the robot. And you also see here the predicted body pose of the user and objects the user is interacting with. I start the video.
Based on observations
I don't
and prior
want the
knowledge
sound.
about
Okay,
object
you see
transitions,
here the moving robot changing or getting new observations, predicting the navigation goal of the user, calculating the best position for itself. But then the robot realizes that the prediction was wrong, so it updates the prediction about the navigation goal of the user, which seems to be somewhere in this area. So the robot chooses the best location for itself here. But while moving there, the robot observes the user entering the room, updates its belief again, calculates the best position for itself. But then the robot again, the user again comes out of this room, and the navigation goal should be somewhere here. The robot then takes the opportunity to overtake the user and arrive at the navigation goal faster than the user, since the prediction was correct in this case. So you see, even if the prediction is sometimes not correct, the robot can adapt its prediction and adapt its behavior and then reach the navigation goal faster than the user, so it would be able to quickly provide service if needed. So to summarize, I'm at the end of my presentation. I presented you two approaches for efficient and foresighted robot navigation in human environments. So first, I explained you how we can exploit knowledge about obstacle classes during path planning. So the robot should not treat objects as static, but it should reason about how to overcome the obstacles. And for that, we use the convolutional neural network to distinguish between different obstacle classes, and then construct a 2D cost grid that encodes the action costs corresponding to the obstacles, and the costs are derived from execution time. And in this cost grid, we can fast compute the robot's path, and this path implicitly contains all necessary actions that need to be carried out by the robot to free its path to overcome the obstacles. And second, I presented an approach that anticipates where users are moving and anticipates navigation goals of users and actually these locations where service of the robot might be needed. For that, we exploit knowledge about object interactions, and we calculate the transition probabilities of user-object interactions and use this to infer users' navigation goals. So we learn sequences of human-object interactions from RGBD data, and then use this learned interaction model to infer the user's navigation goal and predict the corresponding path to the objects. And the robot can then generate foresighted user-friendly navigation behavior by also taking into account constraints derived from human comfort during navigation. So as I showed you, the robot is able to position itself close enough to the user so as to provide service quickly if needed, while avoiding interferences during navigation with the user. Thank you. That's the end of my presentation.